Hi, my dear students. Today we will learn about field due to a polarized object. Okay? Field due to a polarized object. Field due to a polarized object. Hi, my dear students. Today we will learn about field due to a polarized object. In our previous lectures, we learned about polarization. There we see that materials can be polar or non-polar. So, if you apply electric field, either the dipoles induced in the material and align along the direction of the field, or the built-in dipoles align along the direction of the applied field. Anyway, the material get polarized due to the application of the electric field. Okay, now in this contest we want to find out what is the field produced by the polarized object. Okay, the first case we discussed about the applied field which causes the polarization. In this section we find out the expression for the field produced by the polarized object. Okay, so here we see that we have a polarized object. That means there are infinite number of dipoles in the material. Okay, but we know that the potential produced by a single dipole. We already learned about electrostatic potential and we discussed it in many contests. Okay, there we find out the expression for the electrostatic potential due to a single dipole. Okay, but in the case of a polarized object, there are so many dipoles. Okay, so by expressing this, individual, the potential due to individual dipoles and extending the concept to the entire dipoles, we can find out the electrostatic potential produced by a polarized object. Okay, once you get the potential, you can find out electric field using the expression E equal to minus gradient V. Okay, that is the procedure we followed in this section. Okay, so first of all, I will show you here a polarized object. Okay, consider a polarized object. Suppose this is the polarized object, and this object there is a dipole like this. There are so many dipoles in this, and one of the dipole is shown here like this. Okay, and the position, there is a coordinate system here. Okay, there is a coordinate system here like this, and this is the origin of the coordinate system. Now we want to find out the electric field at a point here. Okay, this is the separation vector. We have to find out the electric field and the scalar potential at this point. Okay, this is our problem. And we know that the electrostatic potential at this point is given by 1 by 4 pi epsilon 0 P dot r cap by r square. Okay, here this P represents dipole moment of this single dipole or individual dipole. Okay, now we want to express this in terms of polarization, because we know that for a large object the polarization is measured using the parameter polarization. This is defined as dipole moment per unit volume. Polarization is defined as the dipole moment per unit volume. Okay, so here this dipole moment, you can write this dipole moment P as small p as capital P. This is the polarization, capital P R prime d tau prime. Okay, because we know that this position vector R prime represent the position vector in this polarized object. Okay, so polarization is a function of the vector R prime, and in the primed system we can represent this elementary volume d tau prime also. So the dipole moment is given by capital P d tau prime. Okay, this is the dipole moment. Now you can substitute that term here. So you get here, this is equal to 1 by 4 pi epsilon 0 capital P of R prime R cap by R square d tau prime. Okay, now this is due to a small elementary volume of the polarized object, but we know that the potential due to the entire polarized object is obtained by the volume integral. Okay, this is the volume integral. So here this capital P, this is capital P. Capital P represents the polarization vector. Okay. Now from this expression itself, so the gradient over the primed system of the separation vector, norm of the separation vector, gradient of 1 by R is given by R cap by R square. Okay, that means we can substitute gradient over primed system for this R cap by R square. Okay, so using this in this expression, you can write this potential due to the polarized object by 1 by 4 pi epsilon 0 volume integral of polarization vector R prime dot gradient over the primed system 1 by R d tau prime. Okay. Now we can simplify further this expression. For that, you can take the identity, the divergence operator over polarization by R cap R. Okay, polarization by separation vector R. You can write this as divergence of polarization vector into 1 by R plus polarization vector dot primed 1 by R. Okay, from this you can see that for this part, polarization dot gradient of primed this, you can substitute gradient over primed system dot P by R minus dot P. This polarization is over always on the primed system, minus 1 by R equals P dot gradient 1 by R. Okay, so you can substitute for this term these two terms. Okay, the next step, I want to simplify this expression. So the potential V of R equal to 1 by 4 pi epsilon 0 volume integral of, next term is this one, P dot gradient 1 by R. For that we can substitute this one. So you can write here gradient over primed system dot polarization by separation vector minus divergence of polarization vector by separation vector R. D to prime. Okay. Now the potential due to the polarized object is given by these two integrals. One volume integral here and the other one here. Okay. Now we can simplify further these two equations. So for this first term we can apply Gauss divergence theorem. That means 1 by 4 pi epsilon 0 volume integral of divergence of polarization by separation vector d to prime. This is equal to, using the Gauss divergence theorem, you can replace this with the closed surface integral. 1 by 4 pi epsilon 0 closed surface integral polarization by separation vector dot dA prime. Okay, well this dA prime represents the surface integral. Okay, so we can replace the first volume integral with this closed surface integral. Okay. Now the potential can be written as 1 by 4 pi epsilon 0 closed surface integral polarization by separation vector dot dA minus 1 by 4 pi epsilon 0 volume integral of divergence of polarization by separation vector d to prime. Okay, from this expression we can see that this potential has two terms. In this first case there is a closed surface integral. In this closed surface integral we can see that this term looks like the potential due to a surface charge density. That means sigma b equal to polarization dot n cap, where n cap is along the direction of the aerial vector. Okay, this first term is electrostatic potential due to a surface charge density sigma b, which is given by P dot n cap. Okay, similarly, the second term looks like the electrostatic potential due to a volume charge density. Okay, let it be rho b. Okay, volume charge density rho b. This is equal to minus del dot p. Okay, here we use the primed system, so you can write like this. Okay, primed system. So the electrostatic potential due to a polarized object can be written as sum of two terms: electrostatic potential due to a surface charge density sigma b, which is given by polarization dot n cap. Okay, or you can write this as P cos theta. Okay, this is P cos theta, where theta is the angle between this polarization and n cap. Okay, similarly, the rho b, the second term, is the electrostatic potential due to a volume charge density rho b, which is given by divergence of the polarization vector minus del dot p. Okay, so the electric field due to a polarized object can be written as the electrostatic potential due to the surface charge density plus electrostatic potential due to volume charge density. Once you get the electrostatic potential, you can find out the electric field using the expression E equal to minus grad V. Okay, now we can think about the physical meaning of this sigma b and rho b. Physical interpretation of bound charges. Okay. Physical interpretation. We already find that the potential, electrostatic potential or electrostatic field due to a polarized object appears like a contribution from surface charge density and a contribution from volume charge density. Okay, these charges are called bound charges. Okay, bound charges. In conductors, we see that there are so many electrons or free electrons which can move throughout the conductor. Once you apply electric field, these free electrons travels from one end to other and there is a current flow. Okay, this happens in the case of a conductor. But in the case of a dielectric, there is no free electrons. Then where we get these bound charges? That is the question. Okay, so for the convenience, assume a uniformly polarized dielectric. Okay, a linear dielectric. I will show you a linear structure like this. Uniformly polarized dipoles like this. Okay, same length. All dipole moments are aligned like this, same length. Then what happens? In this case, we can see that this polarized objects looks like the head of one dipole moment is cancelled by the tail of the other one. Okay, that means you know that the dipole is represented by minus negative to positive. So here this is negative, this is positive, this is negative, this is positive, like this. Okay, so what happens? The head of the one dipole is cancelled by the tail of the other, except at the boundary. Okay, so this is looks like a long dipole like this with two charges at both ends like this. Okay, so this polarized objects looks like a single dipole, a single long dipole like this in this form. So here you can see that there are two charges separated by a distance. But we know that we can't remove these charges because these charges are bound charges. Because in this case, all the charges are associated with an atom. In the case of a dielectric, all valence electrons are tightly bound to the atom. They can just move around only about the around the atom. It can't move throughout the material. Okay. In this context, for a uniform polarization, a net charge resides at the ends of this polarized object. So this figure, this object looks like a long dipole with two charges separated by a distance d. Okay, here these charges are called bound charges because we can't remove, or these charges can't be flow through the body. Okay, so these are called bound charges. Now we can think about another example. Consider a dielectric in the form of a tube like this. Okay, polarized dielectric in the form of a tube. Now, suppose we cut a small section of this tube like this. This is a small section of this tube. Area of this section, area of cross section is capital A, and suppose this is the distance d. In the case of a uniform polarization, here this body, in the case of uniform polarization, the dipole moment of this tiny piece, okay, dipole moment of this tiny piece of chunk is given by polarization into area of cross section into d. Okay, here we assume the dielectric is along the direction of the polarization. Okay, the tube is considered along the direction of the polarization. This is the direction of the polarization. Okay, so once you cut a small piece from this tube, the dipole moment of this tube is given by this polarization into volume, because we know that dipole moment per unit volume is called polarization. Polarization into volume. Volume of this small piece of tube is given by area of cross section into length of the tube. Okay, this object looks like two charges separated by a distance like this. Okay, separated by a distance. This is the dipole. In this context, this is the dipole. The dipole moment is given by P into A into D. So you can see that the charges reside, the bound charges reside on this surface of the polarized object in the case of uniform polarization. Okay, we discussed here uniform polarization. In the case of uniform polarization, the charge resides only on the surface of the polarized object, because you can see from here that the figure itself gives you the idea. The head of one of the dipole is cancelled by the tail of the other. So the dipoles inside the material is mutually cancels out, and the charge resides only at the surface of the body. So that looks like two equal and opposite charges separated by a long distance. This is called a dipole, and so there is a dipole moment. This dipole moment is produced by a surface bound charge. This dipole moment is given by here this P into A into D. Now suppose that in this case of the chunk or a piece of the dielectric, the bound surface charge density sigma B is given by Q by A. This is the bound charge on this chunk of dielectric. Okay. Now suppose that this chunk is cut by a slight slanting position. That means we take a piece of this chunk like this. Okay, so here the polarization is along this direction because we already assumed that the tube is along the direction of the polarization. But here the aerial vector is points along this direction, n cap. Okay, suppose the area of this cross section, this slant part is represented by A end. Okay, so in this context, the surface charge density, the bound surface charge density sigma B is given by Q by A end. Okay, A end means aerial vectors, this aerial vector. Here, this is equal to the polarization vector, the component of polarization vector along the direction of this aerial vector. So you can write here P dot n cap. Okay, this is the bound surface charge density of a polarized object. In the case of uniform polarization, the bound charge resides only on the surface of the dielectric. Inside the body, all the charges mutually cancels out in the case of uniform polarization. Now, consider the case of non-uniform polarization. Okay, in this case, the polarized object, a negative divergence of P pile up negative charge inside the body. For example, negative P means the polarization vector is like this, diverging polarization like this. So the dipole moment orient from here to here. Okay, corresponding positive charge on its outside. So the case of a diverging polarization, there is a net negative charge inside the body. Okay, so here there is a volume charge density. Due to the non-uniform polarization, there is charge resides inside the polarized object. So the charge reside inside the body is given by volume integral of rho b d tau, where rho b represents volume bound charge density. Volume bound charge density. Okay, this is called bound charge because we know that these are not free electrons, they are associated with the dipole moment. Okay, so there is volume integral of rho b d tau. This should be equal to the equal and opposite to the charge which is moving out from this body. Okay, that means this is equal to minus surface integral of polarization into dA. Okay, that means the negative charge resides inside the body, that much equal and opposite charge pushed out of the body. Okay, so the equal and opposite is represented by this equal and minus sign. Okay, P dot dA. Now you can apply Gauss divergence theorem here and you can see that this is equal to minus volume integral of del dot P d2. Okay, that means we can see that the bound charge density, volume charge density, rho B is equal to minus del dot P. Okay. Hope that you understand the concept here. Here we studied the what happens with dielectric when there happens polarization. So here we discussed this in the two cases. In the first case we assume uniform polarization. There we see that the charge resides only on the surface of the dielectric material. All the charges inside cancels out and there is a bound surface charge density. This is called bound charge because these charges cannot be moved throughout the material but they resides only on the surface. Okay. Similarly, in the case of non-uniform polarization, there is the accumulation of charges inside the polarized object. If the divergence is, if the polarization is diverging, that means there is a negative pile-up negative pile-up charge inside the polarized object. The volume charge density is obtained from the expression of the amount of charge which is pushed out of this polarized object. The pushed out charge is given by the surface integral of P dot dA. This charge is equal and opposite to the charge which resides inside. So we can put here a minus sign. Minus surface integral P dot dA. Now you can apply Gauss divergence law and then you can see that this volume charge density is given by minus del dot P. Okay, so if you need the electrostatic potential or electric field due to a polarized object, you have to find out the surface charge density and the volume charge density. If the object is uniformly polarized, then there is only the surface charge density. If the object is non-uniformly polarized, there will be the volume charge density also. Okay. So, I think I can wind up now. Here we learned about the electrostatic potential due to a polarized object. And we see that the electrostatic potential can be written as the potential due to a surface charge density and the potential due to a volume charge density. And then we find out that these charges are bound charges. They can't move throughout the polarized material. They can reside only on the surface or inside the material, depending on the context. If the material is uniformly polarized, the bound charge resides only on the surface and the surface charge density. If it is non-uniformly polarized, the bound charge resides both in the surface and inside the material. So there is both the surface charge density and the volume charge density. Okay, so learn well. Thank you.